All right. Hello, everyone. So if you couldn't make the real-time lecture today, I'm going to post a version of that lecture now, which is obviously what you're listening to. Since I didn't know how the class was going to go, since it was the first time we did it, I didn't record this live lecture. From here on out, I will, though, so you will have the same lecture as everyone who attended the live class. But for this one lecture, I'm just posting kind of an abbreviated recording of my lecture, just because I didn't know how things were going to go. So apologies for that, but from here on out, you will have the same lecture as everyone else, I promise. So give me 1 second, and I'm going to show you my slides. So hopefully we'll see. You should be able to see these slides. Obviously we're in week 10 now. I didn't update the number, but we're going to discuss a thing called capacitors today. This references section 20.5 in the textbook. The other thing I'm going to do is assign 4 mastering physics problems. I'm going to assign mastering physics problems in smaller sets that kind of go along with the lecture, so it's easier to kind of know which topic different problems relate to. So the book chapter is 20.5, and you will see a mastering physics set with today's date posted now. So what are these things called capacitors, and why are they important for what we're going to do? So basically, this thing in physics called a parallel plate capacitor, it's an arrangement of 2 conducting plates that hold a lot of charge. So one plate has a lot of positive charge. The other plate has a lot of negative charge. And in between the plates, it creates an electric field. And that electric field ends up being fairly uniform. So what you'll see here is that by uniform, I mean that the electric field is constant in strength and fairly constant in direction. It points directly from the positive plate to the negative plate. Our main reason for talking about such a system is that this is going to relate to us. Our main goal in discussing electricity is to learn the principles behind nerve signal conduction. And this capacitor structure is a model for a lot of different things in nature and in engineering, but in particular, it's a very good model for how charge builds up on the outside and inside of a cell membrane. So here you can kind of think of the bilipid layer in a cell membrane as being our 2 different plates of charge. There's an ion separation from one side of the plate to the other. And that ion separation leads to one side of the cell membrane being positively charged, usually where the sodium ions are accumulated, and the other side being negatively charged. So this builds up an electric field inside the cell membrane. And as we'll see in a few weeks, it's modulations or changes in that electric field that encode the nerve signals that propagate down our neurons. So we want to figure out kind of, for today, what this electric field inside these plates looks like, and also how we can predict the strength of that electric field and its shape, etc. As for an example from like engineering or medicine of a parallel plate capacitor, you can think of kind of these defibrillator panels for starting someone's if their heart goes into, I think it's arrhythmia, but biologists or you pre-med majors can correct me. If you need to restart someone's heart with an electric jolt, the 2 panels on a defibrillator can be thought of like parallel plate capacitors, where one plate has a lot of positive charge, the other plate has a lot of negative charge, and there's a big field between them. And when you touch them to a person's body, the charge accelerates through the body due to that electric field. So what does this field look like? Well, as I said, it's uniform. And what that means is it's constant in strength and direction, at least near the center of the plates. Near the edges, this isn't true, but for most of our problems here, we're considering only the kind of points near the center. So here we have like a zoomed in version of our positive and negative plate. And we can see each positive charge on the plate creates its own electric field that points directly away from that positive charge. Similarly, for all the negative charges, it creates a electric field that points directly towards each negative charge. But the net effect is that the positive and negative charges, or that all of these electric fields, the horizontal components, meaning the components along this direction, all tend to cancel, just leaving the vertical components. And for both positive and negative charge, those vertical components add together and point towards the negative plate. So horizontal components cancel, and we're left with just these components perpendicular to the plate. And if we work this out at kind of all the points inside the plate, what we'll see is that the net total electric field looks like this. At every point, it's more or less uniform in strength and pointing all in the same direction. I have a little simulation I'm going to show you guys, so give me 1 second here to pull that up. So I am going to share a Google Chrome window. Hopefully you guys can see this. So here, this is a electric field simulator from University of Colorado. It's a nice little electric field game you can play. So I sent you guys a link class-wide in email, so you could open this up and play around with it if you want. What this allows me to do is take some positive charges and negative charges, throw them out here in space, and it graphs their electric field. So the direction of the arrow shows the direction of the electric field, and the kind of brightness of the arrow is kind of a measure or visualization of how strong the electric field is. As you can see, we could throw on some charges here, like I'll do one positive and one negative charge. And we don't really have a uniform electric field that's kind of curving in space. But if I keep adding more and more charges, let's add another positive and negative set here. And maybe another one over here. You can see that kind of in between, especially near the center of this charge distribution, the electric field has started to get kind of straighter. It's still not really perfectly straight, but let's add in a few more. And the more and more I add in, kind of approximating like a big plate of charge, the more straight and uniform that field in between the charges gets. Obviously out here, it's not straight or uniform, it's still curving. But in between the plates, it becomes uniform and straight, pointing directly from positive to negative. This other, here I made a big one earlier to show you that if you really add in a lot of charges here, the field really does get very straight and uniform. So because all those horizontal components are canceling out. So you guys can take this simulation and try to play around with it if you would like after you watch this video. Kind of fun by certain definitions of the word fun. So, all right, let's go back to the slides now. So that's kind of meant to show you why the electric field inside this plate region ends up becoming uniform. So you can think of it in terms of vector components canceling, or like the electric fields of all those charges. As you add them up and add in individual charges, the field in this region ends up becoming straighter and uniform in strength. So that's kind of gives us the direction of the field inside these plates. For us, we could think of this as the two sides of our cell membrane. So the region in here is really the region inside our bilipid membrane layer. So we have this strong uniform electric field due to this ion separation from one side of the cell membrane to the other. So we know its direction. How do we find its strength? So this is something that in order to find the strength of the field, you really need calculus to do that. So I'm going to just give you the result, and hopefully it seems reasonable. So the strength of this electric field in units of newtons per coulomb is proportional to the charge we have on the plates. So in our model, the charge on one plate and the other are always going to be equal in magnitude. One will have a negative sign, one will be positive, but we're going to take the magnitude, that means just the number, not the sign. So we're going to take a positive, or you could think of it like the charge on the positive plate here in the numerator. The negative plate will be equal, but with an opposite sign. So that's in the numerator because more charge on the plates means will make the electric field inside in the inside region stronger. The other thing this electric field depends on is the area of these plates. So a smaller plate area, A, so that would be like, these could be like square plates or circular plates, but we're looking at them from the side here in this picture. So whatever shape they are, if we take their area, the smaller that area means we concentrate the charge more and we get a stronger electric field in between the two plates. So bigger area would mean a smaller electric field. Smaller area means a bigger electric field, so that appears in the denominator. The last number here, this curly letter E, is an experimental constant that is used to take this from being a proportionality and make it an inequality. That constant is actually the Greek letter, lowercase letter epsilon. It's called the permittivity, and basically it's a measure, it depends on the material you have between the two plates. Some materials will make the electric field inside the plates weaker, others will make it stronger. So this is kind of a material constant. The bigger it gets, the lower the electric field inside the plates. For most of our problems, we're just going to be using the permittivity of vacuum or of air. So I'm going to give you that number here. In SI units, it's 8.85 times 10 to the minus 12 units are coulomb squared per Newton meter squared. So that we get units of electric field on the other side of this equation here. So it's also related, though I'm not going to go into why, it's related to the force constant from Coulomb's law. So if you're interested, epsilon naught is 1 over 4 pi times k, the force constant, 9 times 10 to the 9. So if we work that out, epsilon naught is 8.85 times 10 to the minus 12. So we could use all this information here to try to, for instance, take some known values from nature and use it to kind of figure out some things we don't know. So the first example I'm going to do with you guys, let me run through a slide here quickly and get to the problem, is actually apply this to the cell membrane. So the electric field inside the cell membrane, so that's kind of in this internal region here, that's basically created by this parallel plate capacitor effect. We have a lot of positive ions all kind of near one side of the cell membrane, a lot of negative ions all on the other side of the cell membrane, and effectively we have two separated plates of charge. And they create this electric field that's strong and uniform in between the two plates, pointing from the positive side to the negative side. The positive side is kind of under normal conditions outside the cell, negative side is inside the cell. And basically this electric field is kind of always there in our cell membranes. And in nerve cells in particular, it's always there. And nerve cells kind of change this electric field in order to, and propagate it down the cell in order to create a nerve signal. So we're going to get there in a few weeks about how we change the electric field. You might know it has something to do with changing the charge around the outside. But for right now, we just kind of want to work with some of these numbers and get the idea that this is why that field exists. So the electric field kind of inside the cell membrane, we have estimates for that, so I'm just going to use that for this problem. It's around 7 times 10 to the 6 newtons per coulomb. So we can use this information to estimate just how many ions we might have accumulated around the outside of a given cell. Here we're going to think about just some kind of normal, like standard cell, not a neuron. So just like some standard, effectively spherical cell. That's important because in order to figure out how much charge we have on the cell, we're going to need to have an estimate for the area of the cell membrane, the surface area of the cell membrane. One of the things to do, so here we have this electric field inside the membrane. If we could estimate the area, surface area of the cell, we could then work backwards to figure out what charge is accumulated along the outside of the cell. From there, we could kind of reason to how many ions we must have. So just kind of what helps us is to find the surface area of the cell. And for this problem, I'm going to just kind of take some ballpark numbers here. Of course, I'm estimating. The radius of a cell, I'm going to take that to be like 50 microns. So that would mean like each cell is around, in diameter, is about 100 microns. It's obviously, it might be a bit of an overestimate or underestimate, but we're trying to just get a ballpark figure here. So if I take that radius of a cell, I can then plug that into the surface area of a sphere, for a sphere, 4 pi r squared, and get an estimate for the surface area of the membrane, cell membrane, 3.1 times 10 to the minus 8 square meters. We can then kind of rearrange this formula, plug that in and solve for the charge. So this charge along the boundary, if it's positive, it gives us the total charge on this side of the boundary, 1.9 times 10 to the minus 12. On the other side of our cell membrane, effectively our other plate in the capacitor, we're going to have a negative 1.9 times 10 to the minus 12 coulombs. From there, if we want to know how many ions we have, each sodium ion lost 1 electron, right? As it's a singly ionized sodium ion. So if we want the number of ions, we can do a calculation kind of like we did with the, to find the number of electrons on the balloon. The number of ions, since they each lost 1 electron, they each have a charge of plus 1.6 times 10 to the minus 19. So if we divide the total charge on the boundary by that charge of 1 ion, we get the total number of sodium ions we have accumulated around the outside of this cell. It's about 1.2 times 10 to the 7, or about 1.2 million sodium ions. So around the outside of an average cell. I mean, it's a ballpark figure, but the main idea of this problem is to give you an idea of what this electric field inside the cell membrane looks like and how it arises from the ions around the cell. They effectively act like the charges on our plates. So that's kind of one example that we're going to keep coming back to over the next few weeks. For the next excuse me one second, I lost the video. Let me go back to my slides. I'm going to go back and do one more problem here. So the other problem I like to give you is a problem from the text. This is example 20.9, finding the electric field inside an air purifier. So if you have an electrostatic like air purifier, like sometimes they make these things that you could have in your home if you have allergies that can suck the dust out of the air, or cat hair, or what have you. This problem in particular talks about them in long highway tunnels. As someone who grew up in northeastern Pennsylvania, the long highway tunnel I know about is the Lehigh Tunnel on the Pennsylvania Turnpike between Allentown and Scranton. So if you're from that area, you probably have seen or driven through this tunnel before. And if you look at the, obviously not if you're driving, look at the road if you're driving. But if you're in a car and driving through this tunnel as a passenger, if you look up towards the ceiling, you'll see these like turbines that are kind of sucking in air. And basically what they're doing is taking air and sucking them in between effectively two charged capacitor plates, though this is a very simplified picture. And what that does is the dust particles in the air have a higher chance to be polarized, and they end up being attracted to one plate or another and pulled out of the stream of air. So dirty air enters one side, clean air enters the other. And this is the basic idea for all kinds of electrostatic air purifiers. So in this example, we're given some numbers for this air purifier. We're effectively told the plates inside the purifier are square or rectangular anyway, with a 38 centimeter length and a 20.6 centimeter width. And we're given the charge on the plates, plus 540 nanocoulombs on the positive plate, minus 540 nanocoulombs on the negative plate. So we want to consider what is, our goal here is to find what electric field is inside the plate that's accelerating these dust particles to one side of the plate and collecting them while the air goes through. So we're effectively being asked for that field inside the capacitor plates. So we go back to our capacitor formula here. Here we're given the charge directly. So this Q plate, that is our 540 nanocoulombs. This charge here is always the charge on the positive plate. The area A is going to be the area of the plates itself. Here we're given their shape. We don't need to make assumptions like in the last problem. So they're rectangular. So we're just going to do length times width. Converting, of course, to meters before we work out the area. Our area ends up being 0.0783 square meters. So plugging in our charge, here I have this as nanocoulombs, but realize when you work out the calculation, you should convert to coulombs, so 540 times 10 to the minus 9. Plug in our permittivity constant for air and our area of the plates. And that will give us an electric field of around 7.8 times 10 to the 5th newtons per coulomb. So again, electric fields in most of our problems 10 to the 5th to 10 to the 7 newtons per coulomb is around the kind of the reasonable range for most of our problems. So that's an you can look and see also how they did this problem in the book. Again, it's example 20.9. So from there, those are the two problems I have for class today. I'm going to stop sharing the screen for a second and just talk a bit about homework moving forward. So basically, I think the easiest way to do homework, since we've lost kind of the group work aspect of the class, which I think is really important, I'm trying to make up for that by taking the homework and breaking it into smaller chunks. So I'm going to be assigning homework based mostly on a lecture by lecture basis. So smaller sets, but you'll know exactly what material they cover. So I want to briefly kind of show you that here. So give me 1 second and I'll pull up a mastering physics window and show you the problems for this class. So you should see here, I've assigned 4 problems. They all relate to capacitor plates. So just to kind of talk you through, to show you how they relate. First problem is you're basically given an area, field, you want to find the charge on the plates. Second problem here, we have, again, 2 plates of charge, except you're given circular plates. So the only thing that's different there is really how you have to find the area. Third problem is, again, circular plates, but we have a charge in between. And that charge is being kind of held up by that electric field there. So from that information, you're given kind of a mass of that plastic bead that has a charge that's being levitated by this electric field. You can take that field and then figure out by the fact that this charge is levitated what that field must be, and then work backwards to figure out what must be the charge on one of the plates inside this structure. The last problem is a conceptual problem relating to capacitors. It's an application of a capacitor system in flow cytometry, which is kind of a way to sort different cells by type in a liquid solution. So it talks you through a little paragraph here about this type of experiment, and then gives you two conceptual questions. This is a kind of an MCAT prep problem related to this material, so I thought it was a good idea to assign it for those of you who are interested in that. But as you read through this, think about it like a capacitor problem. And these will be due on Wednesday before, these will be due on Wednesday, the day of our next class. So I highly suggest that you try to do these problems as soon as possible after the lecture, because it'll just be harder to keep track on what the material relates to. Otherwise, I think with us being separated and everything. As far as things go, I hope everyone is staying safe and healthy, and hopefully we'll all get through this sooner rather than later. If you have any questions about exams or how grading is going to work, I'm still trying to figure it out as I go along, but I'm happy to help. So feel free to email me or get in touch. If I don't hear from you though, I will be having office hours tomorrow for this class, I think at 11 a.m. So if you have questions on any of these problems, I'll send you a link to kind of like a Zoom office hour session. So if you have any questions, you can feel free to sign in then and we could talk about them. Anyway, thank you for listening. I hope this helps. If you have any suggestions for how, this online thing, how I can do it better or anything, just let me know. From here on out, I will just be posting a video of the live lecture though. So from here on out, you'll have the same lecture as everyone else. So thank you all. I'm going to stop recording now, and I will talk to you on Wednesday.